Okay, so I just want to quickly take a minute to talk about the types of forces that we're going to see here. Oops. And so, write it down. Types of forces we might see. Okay, so if you remember in last class, we spent some time and we talked about the fact that there's four fundamental forces in the galaxy. Okay, in reality, we only really experience the force of gravity and the electrostatic force on a daily basis. So essentially, if it's not gravity, it's probably an electrostatic force. So, for instance, the normal force is an electrostatic force, right? And it is just surface resistance, essentially, is how we can look at it. Surface resistance. And we already covered this in another class, but I just want to review it. Okay, so if I have an object sitting on a surface, we're always going to have gravity acting on that object. It's a special case, right? So it's mg. In fact, we usually in IB refer to this as weight. So W equals mg. In other physics courses, you might call it force and gravity. Force and gravity and weight are an interchangeable term for the same thing. Okay. The equal and opposite force, that should aim straight up. It's a little hard to draw straight lines here, unless I do this. There we go, that's a little nicer. Okay, the equal and opposite force on that brick is called the normal force. And what causes the normal force again? Yeah. So the normal force is equal to the opposite of the force of gravity. Okay, remember the negative just means direction. Okay, so for an object that is not accelerating, it's sitting still on a surface, it's upward. And you're right, the cause of the normal force is the electrostatic repulsion between these two surfaces at microscopic levels. Okay, so that's one type of force you might experience. Okay, one that you guys were asking about is the force of tension. And again, tension is also an electrostatic force, but this is the pulling force in a taut cable or rope. Okay? So we take this concept here of a box on a surface. We can oh dear, not sure what just happened. Just a sec, guys, sorry about that. Just want to fill you, please. It does not want to select this thing. There, maybe now. There we go. Okay, sweet. So if instead of having that sitting on a surface, if what we have instead is we have it hanging from a rope. Lines here. We will still have our force of gravity aiming down, all right? But if we put a rope up here, what does a rope look like? I think a rope looks kind of like that. Okay, so there's our rope, all right? And we'll imagine that this this block is hanging from a rope. I suppose a rope actually would come from the top of it. There, like that. Okay, so there's our rope. This object's hanging from rope. We have Fg aiming down. The pulling force in the rope, I should start calling this weight. That's what IB does. Okay, so what we would have is we would have an upward equal and opposite force in the rope here, and Ft would be equal to the opposite of weight. Okay, so that's a tension force. It's a pulling force in a taut cable. What causes that? Again, that's an electrostatic force. Okay, so electrostatic attraction within the matter of the rope. So So the matter making up the rope. Then the matter making up the rope or cable supplies that force. Now in a case like this, what would happen to the force of tension if we increased the weight of this object, if we increased its mass? Tension force would also increase, right? Well, eventually it would probably break. Yep, that's right. What do we call a force that automatically increases in response to something like added weight or added mass? Yeah, it's a reactive force. So the normal force is a reactive force, right? It gets larger automatically. And tension force can be a reactive force. Eventually you're going to have a snap here. Now here's a question. What if tension force gets larger than the weight? What happens then? If I apply a larger... Yeah, it would lift it. That's right, it would lift it. If my tension force grows larger than my weight, right, there's a net upward force, and you have an acceleration in the upward direction. Does this object have to be sitting still if tension is equal to weight? No, because the forces would cancel out, but remember, an object stays in motion or at rest unless acted upon by an unbalanced force. So let's say this is a perfectly counterbalanced system. So, you know, you might see this in something like an elevator, right? So let's say you have this here, and oh, I see what you have to do. You have to do it beforehand. Okay, sorry. Let's fix that. I can't erase it that way, but that's okay. Figuring it out as we go. We're still good. Let's try that one more time. Let's say we have... Okay, anyway, whatever. I'll just draw it with a pen. Okay, so we have an elevator here. Okay, we have a big pulley, big round pulley system. Okay, what you might find is an exactly equal mass in this direction. Okay, so you have FG down. Oh, you guys can't see that. I can see it on mine. It's just hard to see. I see, I get it. Okay, I'll fix that. There. Okay, so this represents a large pulley that can turn. Here's a cable. Okay, here's two masses, right? Say this might be an elevator and this might be a counterweight. These both have Fg, and you can see that if these are equal, so if I look here, what the pulley is essentially doing is it's changing the direction of the tension force, right? So I'm pulling down over here, and that's transmitted through this cable, and it's providing an upward pull here. Okay, and if I look at this the other way, this downward pull of Fg over here provides an upward pull over on this side as it's traveled over. So essentially, the net force on this whole system equals 0. Now these could be extremely heavy. We could have a very low friction here, and it would not take very much force, right, additional force, to get this to go into motion. A little push, right, would throw it out of balance and it would start to move, okay? So you don't need a very large motor to move an elevator as long as it's got counterweights on it, okay? Does that make sense? True, that's right. Well, yeah. Usually I think elevators actually, don't quote me on this, but I believe they have brakes rather than another motor to slow them down. But I could be wrong on that. But yeah, you're right. This is a large, massive system, and so once it gets moving, it then has inertia that you're going to have to deal with, right? Right, so exactly. So there's a normal force here too if you want to get really technical. So essentially on the top of the pulley, you have 2 times Fg pulling down, right? So 2 times Fg pulling down, and then you have a normal force on the top of the pulley that's equal and opposite pushing up, okay? And you can really go down the rabbit hole in analyzing forces if you want, but that's what's going on. we treat them all the same regardless of what kind of forces they are, right? Doesn't matter if it's a push or a pull. So a few more. You might have a compression force. So compression force, it's not quite considered to be the same as a normal force, although really it's essentially the same. But imagine we have something like a sign for a restaurant. Happy Guys Fish and Chip Shop, okay? And here's the side of a building, right? What you might have is you might have a cable attached here, and you might have a rod here, okay? So this is a rod or a pipe, and this is a cable. Now this will stay suspended here, but it's interesting. Now we have to think about how are the forces going to work in a system like this. So you're going to have an angle here. You're going to have a downward force like that, right? You must have a tension force like this, and you're probably going to have a compression or pushing force back in that direction, okay? The net result of all of these forces should be what value? 0, right? Now we have to look at something else here, and that's the fact that that there's some components going on as well. Okay, so you're going to have a component, black, yellow. So you're going to have a component of Ft aiming off in this direction, and we would call that Ft cosine theta, right? It's a component of this overall tension. Does that make sense? And that's pulling towards the wall, and you're also going to have an upward component as well. That would be here. Okay, and this component would be what? How would I name this component? This upward one. Ft, opposite angle. So, sine theta. And here's just Ft prime, or the Ft overall. All right, so now let's look at how all these forces balance out. What is the only upward force in this system? Ft sine theta. So what must happen then is that Ft sine theta, being that it's an upward force, must be equal to what? Good. Or weight if we want. And then you can't get away from having this component here, right? So Ft cos theta has to be equal and opposite to good. We just write negatives to mean that they're aiming in opposite directions. So that's how you'd analyze something like this. That's what a compression force would mean, okay? Does that make sense? And then with numbers, if I put mass in here, right, everything else should, you know, sort of work itself out. Yeah, so this would be like, you know, I guess very basic engineering. If you were able to calculate these sorts of things, you might be able to work it out into analyzing the forces at work on a bridge, or, you know, or a crane or whatever. I think the day-to-day work of an engineer is probably all automated by this point in time. But at one point, yeah, people probably worked this out with pen and paper, right? A few other ones that we should talk about while we're at it. Going back to my proper color here. Frictional force. Again, all these forces up here, they're electrostatic. Good, and so is a frictional force. So what causes a frictional force? Yeah, exactly. Is the resistance to motion, resist. Totally, my spelling is a little rough here. Thank you. I'm just spelling secretary. Friction is the resistance to the sliding, I guess, the sliding of one surface across another. Okay? And what's actually at play is if you were to look at the very bottom of two surfaces, even if they seem to be smooth, if we were able to magnify them, and look in there really closely, you'd see that they're quite jagged, right? Even things that appear to be super smooth are jagged. So you can imagine if one object is going to be slid across another, so we're pushing this to the right, there's going to be a resistance or a reactive force, and that's because at the microscopic level, all of these little jagged points, number 1A, have to bump across one another. So you almost have to have like a little, if you want to think about it, a little lift. Every time you're going to move this forward a little bit, it has to bump over and catch into the next teeth. So there's like a lifting aspect to that. Okay, and the reason these don't just like slide by each other and knock, the tops off is there's electrostatic resistance there between these two surfaces. So that's the basis of friction. And it should make sense if I have a heavier object, if the mass of this gets really large, okay, the downward force gets greater, and these are jammed even closer together, and therefore the lifting that has to be done as this surface bumps along gets larger. So friction goes up as you increase mass between two surfaces. Yes? Frictionless, I don't think you can engineer something to be frictionless. Because there's also electrostatic attraction going on here as well. So yes, there's resistance, but there's also attraction, right? Like, if this happens to have a very slight negative charge, even momentarily, that will induce a slight positive charge on the other side, and there'll be a little bit of an attraction between them as well. So that has to be dealt with. So can you engineer friction-free surfaces, Brianna? I don't think so. Thank you. Mm-hmm. Mm-hmm. So there's just a few other forces I'm not going to mention now, but there's like electrostatic, there's magnetic force. Are you texting someone that's out in the hallway? Okay. And just off the top of my head, there's also like umbrella forces, for instance, centripetal force, which we'll study in a little bit. It's not a force on its own, but it describes forces that cause circular motion. Other than that, there's probably some that I'm forgetting, but that's kind of what we'll be dealing with. Okay?